You think you're bigger than an atom. You think an atom is small and you are large. You think size is real, that there's an actual difference between big and small, between tiny and enormous. Richard Feynman would tell you you're wrong. Not sort of wrong, completely, fundamentally wrong. And here's the thing, he can prove it. Size isn't what you think it is. It's not a property of objects. It's not something things have. Size is a relationship, a comparison, an illusion created by the particular scale at which you happen to exist. Let me show you what I mean. Imagine you're an ant, a tiny ant crawling across your kitchen floor. For this ant, a crack in the tile is a canyon. A drop of water is a lake. A crumb of bread is a boulder. The distance across your kitchen is an epic journey that takes hours. Now, is the kitchen actually huge? No. You walk across it in seconds. For you, it's just a room. So which perspective is correct? Is the kitchen big or small? Here's the answer. Both. Neither. The question doesn't make sense without specifying big or small compared to what. The kitchen is big compared to the ant. Small compared to your house. Tiny compared to your city. Microscopic compared to Earth. Invisible compared to the solar system. Size is always relative. Always a comparison. Never an absolute property. Feynman loved this. He loved pointing out that our sense of scale is arbitrary, that we think we're medium-sized because we're us, but there's no such thing as medium in the universe. There's no natural center point. We just happen to exist at one particular scale, and we call that normal. But watch this. It gets stranger. Because it's not just that size is relative. It's that the laws of physics change depending on what scale you're looking at. The universe behaves completely differently at different sizes. Let me give you an example. Water. You know water. It's wet. It flows. Pour it into a glass. It takes the shape of the glass. Splash it. It makes waves. That's water at your scale. But shrink yourself down. Get really small. Become the size of an insect. Now water isn't wet anymore. Water is sticky. Thick. Almost solid. An insect that falls into water doesn't sink and swim. It gets trapped. The water molecules cling to it. Surface tension, which barely matters to you, is an overwhelming force to the insect. The insect can't just shake off water. It's like being covered in glue. Why? Because at small scales, surface forces dominate. The ratio of surface area to volume changes everything. You're big, so your volume is large compared to your surface. Gravity, which acts on your whole volume, is the main force you feel. But an insect is small. Its surface area is huge compared to its volume. Surface forces, like the stickiness of water, become dominant. Same substance, different scale, completely different behavior. Feynman would ask his students, why can't you make a really tiny person? Like, why can't you shrink a human down to the size of an insect? And the answer isn't just because we don't have the technology. The answer is because it wouldn't work. A tiny human would die instantly. Here's why. Your body is designed for your scale. Your bones are thick enough to support your weight under Earth's gravity. Your heart is strong enough to pump blood through your body. Your lungs have enough surface area to absorb oxygen. But if you shrunk to insect size, everything would break. Your bones would be way too thick, way too strong. You'd be carrying around massive structural supports for almost no weight. You'd be like a building made of steel beams, but the size of a dollhouse. Total overkill. Meanwhile, your heart would be too weak. At small scales, viscosity matters more. Blood becomes harder to pump. Your heart, designed for your current size, couldn't handle it. And your lungs? Disaster. You need a certain amount of surface area to absorb enough oxygen to power your body. If you shrink, your surface area shrinks faster than your volume. You'd suffocate. You couldn't breathe fast enough to stay alive. This is why insects can't be the size of humans. It's not just impractical, it's physically impossible. An insect scaled up to human size would collapse under its own weight. Its exoskeleton, perfect for small scales, would shatter. Its breathing system, which works by diffusion through tiny tubes, couldn't deliver oxygen to a large body. It would suffocate. Physics changes with scale. The laws are the same, but which laws matter changes dramatically. At your scale, gravity dominates. At insect scale, surface tension and viscosity dominate. At atomic scale, quantum mechanics dominates. Different scales, different physics. Now, Feynman loved thinking about this in the other direction too. What if you got bigger? What if you were the size of a building or a mountain? Same problem. Your bones would need to be thicker and thicker to support your weight. Eventually, you'd need bones so thick you couldn't move. Your heart would need to pump blood so far against gravity that it would fail. Your legs would be massive pillars just to keep you upright. There's a reason the largest animals on Earth are whales. They live in water. Water supports their weight. On land, there's a maximum size for animals, determined by the strength of bone and the force of gravity. Get too big, and you can't exist. Physics says no. Here's what Feynman realized. Every scale has its own rules, its own constraints, its own possibilities, and the universe doesn't care which scale you think is normal. You think you're normal-sized, but to an atom, you're unimaginably vast. To a galaxy, you're unimaginably tiny. There is no normal. There's just different scales, each with its own physics, its own phenomena, its own logic. Let me take you deeper. Because Feynman didn't stop at insects and humans. He thought about atoms. He thought about the smallest scales possible. And he discovered something beautiful. At the atomic scale, size becomes almost meaningless. Here's what I mean. An atom is mostly empty space. You know this. The nucleus is tiny, sitting in the center. The electrons orbit far away. If an atom were the size of a football stadium, the nucleus would be a marble on the 50-yard line. Everything else? Empty. So when you touch a table, you're not really touching it. The atoms in your hand and the atoms in the table never actually make contact. They get close, and the electromagnetic forces between them push back. You feel resistance, you feel solid. But it's not solid. It's force fields pushing against each other. There's no contact, no touching, just forces. Which means solid isn't real. Hard isn't real. The table feels hard because the forces are strong at your scale. But zoom in, and it's mostly nothing. Here's where it gets wild. Feynman asked, how much information could you store if you could write at the atomic scale? If you could manipulate individual atoms, and he calculated it. Every book ever written, every photograph ever taken, every piece of human knowledge, all of it could fit in a cube the size of a dust speck. All of it. The entire Library of Congress could be written on the head of a pin with room to spare. Why don't we do this? Because we exist at the wrong scale. Our fingers are huge. Our tools are huge. We can't manipulate individual atoms easily. But there's no law of physics stopping us. It's just an engineering problem. And Feynman knew this. He gave a famous lecture in 1959 called "There's Plenty of Room at the Bottom." He told scientists, look down, look at the small scales. There's an entire world down there, an entire frontier. We're ignoring it because we're stuck at our scale. But we don't have to be. We can build tools. We can see smaller. We can manipulate smaller. And when we do, we'll unlock technologies we can't even imagine yet. He was right. Today, we have nanotechnology. We can move individual atoms. We can build structures one atom at a time. We can store information at scales Feynman dreamed about. We went down, we explored the small, and we found exactly what he said we'd find. A whole new world with its own rules. But let me tell you something even stranger. At small enough scales, size stops being definite. At the quantum level, particles don't have exact positions. They don't have exact sizes. An electron isn't a little ball. It's a probability cloud, a region of space where the electron might be. Ask where the electron is, and nature says, I don't know until you measure it. Ask how big the electron is, and nature says, that question doesn't make sense. The electron is a point particle with no size, zero radius, but it also has a wavelength which spreads out over space. So is it big or small? Neither. Both. The question assumes something that isn't true. It assumes the electron is a classical object with a definite size. But it's not. It's quantum. And quantum objects don't follow the rules you expect. Feynman spent his life studying this. He developed a whole new way of doing quantum mechanics using path integrals and diagrams. And what he discovered is that at the quantum scale, particles don't have definite paths. They don't go from point A to point B in a straight line. They take every possible path at once, all of them, simultaneously. And these paths interfere with each other, creating the probabilities we measure. This is real. This is how the universe actually works at small scales. Size, position, path. All of these become fuzzy, indefinite, probabilistic. Your intuition, which tells you things have sizes and positions, is completely wrong at this scale. Now, let's go the other direction. Let's go big. Really big, galactic scale. Because Feynman understood that size is an illusion here too. When you look at a galaxy, it looks like a thing, a structure, an object with a size. But zoom out. Look at the universe. Galaxies are just dots, tiny specks in an incomprehensibly large expanse. And here's the shocking part. The distances between galaxies are growing. Space itself is expanding. So is the galaxy getting bigger, or is space between galaxies getting bigger? Both. Neither. The question assumes space is fixed. But space isn't fixed. Space is dynamic. It stretches. So when you ask how big a galaxy is, the answer depends on when you're asking. The distance between 2 points in space changes over time. Not because the points are moving through space, but because space itself is changing. Size becomes relative, not just to what you're comparing to, but to when you're measuring. Here's what Feynman would tell you. There is no absolute size, no absolute scale, no privileged perspective. You are not big or small. You're just at one scale among infinite possible scales, and every scale reveals different physics, different phenomena, different truths. When you're small, surface tension matters. When you're big, gravity matters. When you're quantum, probability matters. When you're cosmic, space-time curvature matters. The universe doesn't have a correct size. It has all sizes. And you, by existing at one particular size, are seeing only one slice of reality, one perspective, one set of phenomena. Let me give you one more example, because this one is my favorite. Feynman loved explaining why you can't have a perfect map. You know the idea of a map, a representation of a place, smaller than the actual place, but containing all the information. But here's the problem. To make a perfect map, you'd need to include every detail, every rock, every grain of sand, every atom. And if you include every atom, your map would be the same size as the place itself. It wouldn't be a map anymore. It would be a duplicate. And even then, it wouldn't be perfect, because the atoms in your map would be different atoms than the atoms in the real place. So a perfect map is impossible. The only perfect map of a place is the place itself, 1-to-1 scale, which defeats the purpose of a map. This is a deep idea. It tells you that information has a physical size, that you can't compress information infinitely, that there's a relationship between detail and scale. Feynman understood this. He understood that every time you change scale, you lose information. You simplify, you abstract, you see different things, and you can't see everything at once. You can look at the forest or you can look at the trees, but you can't look at both simultaneously. Your brain has to choose a scale. Here's the beautiful part. Feynman wasn't bothered by this. He was delighted. He loved that the universe had this structure, that different scales revealed different things, that you could spend a lifetime exploring one scale and never run out of discoveries. He famously said, "There's plenty of room at the bottom," but he could have just as easily said there's plenty of room at the top, or the middle, or anywhere, because every scale is rich with phenomena waiting to be understood. Think about what this means for you. You walk around thinking you understand size. You think a car is big and a marble is small, but that's just your scale talking. To a bacterium, a marble is a planet. To an astronaut in space, a car is invisible. Your sense of size is an accident of evolution. Your brain evolved to operate at human scale. To judge distances, you can walk. Sizes you can grab. Speeds you can run. It did not evolve to understand atoms or galaxies. So when you try to think about those scales, your intuition fails. Your brain gives you nonsense. And that's okay. Because Feynman showed us we don't need intuition. We have mathematics. We have measurement. We have tools that let us explore scales we can't directly perceive. We can see atoms with electron microscopes. We can see galaxies with telescopes. We can calculate what happens at scales far beyond our senses. And what we find is that the universe is the same at every scale and completely different at every scale. The same fundamental laws apply everywhere. But the phenomena those laws create change dramatically with size. Let me bring this all together. Size is not a property of objects. Size is a relationship, a comparison, an emergent phenomenon that only makes sense when you specify a reference frame. You are not big or small. You are big compared to atoms and small compared to planets. And those are both equally true. The universe doesn't have a natural scale. It doesn't prefer one size over another. It contains all sizes. From the Planck length, the smallest possible distance, to the observable universe, the largest structure we can see. That's 60 orders of magnitude, 60 powers of 10. And at every point along that spectrum, there's something interesting, something worth studying, something that behaves in ways you wouldn't expect. Here's what Feynman wanted you to understand. When you think something is big or small, you're revealing something about yourself, not about the object. You're revealing what scale you're adapted to, what size makes sense to your evolved primate brain. But the universe doesn't care about your brain. The universe operates at all scales simultaneously, and each scale is equally real. The physics that governs an atom is just as valid as the physics that governs a galaxy. Neither is more fundamental, neither is more true. They're just different regimes of the same underlying reality. Watch this. Feynman loved to point out that we're made of atoms. You know this intellectually, but do you really get it? Every part of you is a collection of atoms. Your skin, your bones, your brain. Trillions upon trillions of atoms, each one following the laws of quantum mechanics, each one mostly empty space, each one held together by forces, not by solidity. You are not solid. You are a pattern, a configuration, a particular arrangement of particles that happens to be stable enough to persist for several decades. That's you. That's all you are physically. A temporary pattern in a sea of quantum fields. And yet, you think, you feel, you experience, you are aware. How? How does a collection of atoms become conscious? How does size, which is an illusion, create something that experiences size as real? Feynman didn't know. Nobody knows. But he appreciated the mystery. He appreciated that we're made of simple parts following simple rules, and yet we emerge as complex beings capable of understanding those rules. That's remarkable. That's genuinely miraculous. Not supernatural, not magical, just deeply, profoundly strange. Atoms which have no awareness, no consciousness, no sense of size or scale, organize themselves into you, and you look down at atoms and try to understand them. The universe studying itself. Matter trying to comprehend matter. That's what you are. A piece of the cosmos that became aware and started asking questions. Why does size feel real when it's just a comparison? Why does solid feel solid when it's mostly empty space? Why do we exist at this particular scale and not some other? These aren't stupid questions. These are deep questions about the nature of reality. And Feynman would tell you the answer isn't to trust your intuition. Your intuition is wrong. Evolution built it for survival, not for truth. The answer is to measure, to calculate, to test, to build instruments that let you see beyond your natural scale, to develop mathematics that describes phenomena you can't directly observe, to accept that reality is stranger than it appears. Here is the key insight. The universe is scale invariant in its strangeness. At every size, something weird is happening. At the quantum scale, particles are waves. At the human scale, time passes at the same rate everywhere, except it doesn't. At the cosmic scale, space expands. At every level, the universe violates your expectations. And that's not a bug. That's a feature. That's how reality is. Feynman embraced this. He loved that the universe was weird. He loved that it didn't make intuitive sense. Because that meant there was always more to discover, always more to learn, always more to figure out. He'd tell his students, I don't understand it either. Let's figure it out together. He never pretended to have all the answers. He just had better questions and better tools for finding answers. Let me tell you about one of Feynman's favorite thought experiments. Imagine you have a machine that can shrink you, really shrink you, down to molecular size. You climb inside, press the button, and suddenly you're tiny. Now you're inside a drop of water. What do you see? Not what you expect. You don't see a smooth, continuous fluid. You see molecules, gigantic molecules, from your new perspective, bouncing around randomly, jittering, vibrating, smashing into each other. Water isn't smooth. It's chaotic, a storm of molecular motion, and it's hot. Not because the temperature is high, but because temperature is molecular motion. Heat is just atoms moving. The faster they move, the hotter it is. At your new scale, you'd feel the impacts. You'd be buffeted by water molecules slamming into you from all directions. Brownian motion, random thermal jittering. This is real. This is happening right now in every drop of water. You just can't see it because you're too big. Your scale averages out the chaos. You see smooth. You feel wet. But that's an illusion. The reality is violent and random. Feynman loved this. He loved that what seems calm at one scale is chaos at another. That smooth is just average chaos. That every property you think is fundamental is actually emergent from smaller scale phenomena. Wetness emerges from molecular properties. Hardness emerges from electromagnetic forces. Temperature emerges from motion. Color emerges from quantum transitions. Everything you experience is a higher level summary of lower level physics. You never see the real thing. You only see your scale's interpretation of it. Here's what this means. When you say something is big or small, you're not describing the object. You're describing your relationship to it. And that relationship is arbitrary, an accident of evolution, a consequence of the particular size at which your ancestors survived. If you'd evolved at a different scale, everything would be different. If humans were the size of ants, we'd have exoskeletons. We'd breathe through tubes. We'd be terrified of water. we'd live in a universe dominated by surface tension and electrostatic forces. Gravity would barely matter. We could fall from any height and survive. We'd build differently, think differently, experience the world completely differently. Same universe, same laws of physics, but different scale means different reality. That's the illusion. You think reality is what you experience, but what you experience is just one narrow slice of what's actually there. Feynman knew this. He knew we're blind to most of the universe, not because we lack the right instruments, though we often do, but because our brains are tuned to one scale, and that scale is a tiny fraction of what exists. So how do we escape? How do we see beyond our scale? Through science? Through mathematics? Through building tools that extend our senses. Microscopes let us see small. Telescopes let us see big. Particle accelerators let us probe the quantum realm. Satellites let us measure cosmic structures. Each tool is a way of accessing a scale we're not built for. And each new scale reveals new physics, new phenomena, new wonders. Feynman was obsessed with this. He talked about looking at a flower. Most people see a flower and think it's beautiful. Feynman would see the same beauty, but then he'd see more. He'd think about the cells, about the molecular machinery inside each cell, about the quantum processes that let the flower convert sunlight into energy, about the evolutionary history that shaped every petal. He'd see beauty at every scale, and the beauty didn't diminish when he understood it. It multiplied. Most people think science ruins the magic, that understanding something makes it less beautiful. Feynman proved the opposite. Understanding adds layers. It reveals deeper patterns. It shows you that there's no such thing as just a flower. There's a flower at human scale, which is beautiful. There's a flower at cellular scale, which is magnificent. There's a flower at molecular scale, which is a miracle. Same object, infinite depths, all equally real. That's what size being an illusion really means. It means there's no one correct way to look at anything. Every scale is valid. Every perspective reveals truth. You're not seeing wrong by looking at human scale. You're just seeing incompletely. Let me give you something to think about. The human body is made of about 7 octillion atoms. That's 7 billion billion billion. Each one is a tiny universe unto itself with a nucleus and electrons and quantum behaviors. You are a galaxy of atoms, a cosmos in biological form. And yet, you don't feel like a collection. You feel like one thing, one unified consciousness. Why? How do 7 octillion separate particles create a single experience? How does size, which is relative, give rise to something that feels absolute? Science doesn't know yet, but Feynman would tell you that's okay. Not knowing is fine. Not knowing is where science begins. You see something strange. You don't understand it. So you investigate, you measure, you test, you build theories, and slowly, piece by piece, you figure it out. That's the process. That's how we learn. We don't need to understand everything immediately. We just need to keep asking questions. Here's the truth. You're not big. You're not small. You're exactly the size you are, and that size only has meaning when compared to something else. A human is large compared to an atom. A human is small compared to a mountain. Both are true. Neither is more true than the other. Size is a relationship, not a property. And Feynman understood this better than almost anyone. He understood that we live in a universe of relationships. Position is relative. Velocity is relative. Time is relative. Size is relative. There are no absolutes except the speed of light and the laws of physics themselves. Everything else depends on your frame of reference. And your frame of reference is arbitrary. You didn't choose to be human-sized. You didn't choose to experience time at the rate you do. You didn't choose to see visible light instead of X-rays. Evolution chose for you. It built you to survive at one particular scale, in one particular environment. And that's fine for survival. But it's terrible for understanding reality, because reality is bigger than your scale, smaller than your scale, stranger than your intuition can grasp. Feynman spent his life teaching people to let go of intuition, to stop trusting their gut feelings about how the universe works, to accept that reality doesn't care about making sense to you. It just is what it is, and if you want to understand it, you need to set aside your assumptions. You need to measure carefully. You need to follow the mathematics wherever it leads, even if it leads somewhere uncomfortable, even if it leads to a conclusion that feels wrong. So what's the conclusion here? What am I trying to tell you? This. Size is an illusion. Not in some mystical sense, in a precise physical sense. The universe doesn't have a scale. It has all scales, and you happen to exist at one of them. That's all. You're not special. Your scale is not special. It's just yours. And when you realize this, when you really internalize it, something changes. You stop thinking of yourself as the center. You stop thinking that human-sized objects are normal and everything else is abnormal. You start seeing the universe as it actually is. A vast spectrum of scales, each with its own physics, each equally valid, each equally real. And you're just a point on that spectrum, a temporary pattern of atoms that happens to be thinking about atoms. Feynman would love that. He'd love that you're asking these questions, that you're pushing beyond your intuition, that you're trying to understand reality instead of just experiencing it, because that's what makes us different from everything else. We can think about thinking, we can study ourselves, we can ask why size feels real when it's just a comparison, and then we can figure out the answer, not through philosophy, not through speculation, through experiment, through measurement, through science. That's Feynman's legacy, not the equations, not the Nobel Prize, the attitude, the approach, the relentless curiosity, and the refusal to accept easy answers, the willingness to admit, I don't know, and then go find out. So the next time you look at something and think it's big or small, remember, you're not describing the thing. You're describing yourself, your scale, your perspective, and there are infinite other perspectives, all equally valid. That's the illusion. Not that size doesn't exist, but that it exists absolutely. It doesn't. It's relative, relational, contextual. And once you see that, once you really see it, you can't unsee it. The universe opens up. Every scale becomes a frontier. Every size becomes a doorway to new physics. And you realize that we've barely started exploring. There's so much more to discover, so much more to understand. Feynman knew this. He knew we'd never run out of questions, never run out of mysteries, because the universe is infinite in its depths, not just in space, in scale, in complexity, in strangeness, and that's beautiful. That's genuinely, profoundly beautiful. We're tiny creatures on a small planet asking big questions, and we're getting answers. We're figuring it out, one scale at a time.